Wonderful. Good morning, everyone, and welcome to today's UNU-INWEH Science Talk. My name is Dr. Rohit Ramchandani, filling in for our regular host, Dr. Miriam Axel. And I am UNU-INWEH's Innovation and Strategic Partnerships Officer. And I'm thrilled to be your host today. For those of you new to Science Talks, our weekly series showcases the exciting research of UNU-INWEH. I'm pleased to share that all our previous Science Talks are available on demand. You can watch the full 2024 series hosted by Professor Grace Aluusanya on our website and our YouTube channel at unu.edu/INWEH/Science Talks. Today's talk, like all others, will be recorded and the video will be made available after the session. We'll conclude with an interactive Q&A, so please share your questions in the Q&A box. Today's speaker is Dr. Pratap Ramamurthy, who is an associate professor in the Department of Mechanical Engineering and the Department of Earth Systems Science and Environmental Engineering at the City College of New York, where he also leads the research cluster on compounded extremes in urban environments at our UNU hub on remote sensing and sustainable innovations for resilient urban systems. He leads a dynamic research lab dedicated to building more sustainable cities by examining the complex relationships between climate, human activity, and the urban environment. His work spans computational fluid dynamics, building energy modeling, environmental fluid mechanics, and the impacts of climate change on cities. Dr. Ramamurthy's research combines scalable field experiments with advanced numerical modeling to better understand how mass, momentum, and energy move through the urban boundary layer. His current projects explore mechanisms that intensify the urban heat island effect and its interaction with heat waves, while also developing practical mitigation strategies to help moderate urban climates. He also collaborates with the NOAA's CREST Center to operationalize remote sensing tools for studying urban environments and leads research on coastal urban boundary layers and their influence on convective clouds and thunderstorms. Please join me in welcoming Dr. Pratap Ramamurthy.
Right. Thank you, Rohit. That was a wonderful introduction. So I'm at the City College of New York, and I'm really excited to be part of the UNU-INWEH hub. So today I'm going to generally just talk about urbanization and climate change, and then look into what are some of the complexities in understanding urbanization, particularly from an urban climate perspective. And also moving forward, some of the interesting results that I have seen from my previous and ongoing research. So to start, when you go online, open your browser, and then type in climate change, image, just show me an image of climate change. It's going to pull up an image, something that looks like this. This is from an ICC report. You have a global climate model, which is telling you how much the temperature is going to change in some future year. And then if you are, let's say, living in Canada, or you're living in New York, you look at it, you're that's about 0.8 degrees Celsius. Okay, I'm kind of fine. And then you move on. But on the other hand, if you type in who will be impacted by climate change, it pulls up this image also from an IPCC report. And the most interesting thing about this image is it starts naming places. And if you look around, all you see is just cities. So this image actually tells you how many days people living in different parts of the world will experience climate change impacts in their day-to-day life. As you could see, like, cities in the tropics, particularly like, in Southeast Asia, and also in like West Africa, and then parts of Amazon, they are going to experience like, a lot more days every year. But the thing now is you actually see like, they particularly go and look at these cities because, cities is where people actually live. So although we talk about, whenever we talk about climate change, global warming and things like that, people take like a very large scale perspective, a larger time frame, a larger spatial scale. But actually climate change impacts, the ones that are going to be most impacted are actually mostly be in cities. Now, if you look at like the whole thing about urbanization, cities overall occupy less than 5% of the land cover. In fact, if you don't count the suburbia and all the ex-urban areas, I think it's probably even smaller, but even conservatively, like less than 5% of the world's total land cover consists of cities. But currently, cities support nearly more than half of the world's population. And this number is going to just like explode in the next 20, 30 years. Like places like India and a lot of parts of Africa are urbanizing very, very, very rapidly. So by 2050, it's expected that nearly like 62 to 65% of the world's population, which is almost two-thirds of the world population, will be living in urbanized areas. Now, already, even by today's standard, like while cities occupy less than 5% of the world's population, nearly like 75, more than 75, around 78% of energy consumption happens in urban areas, and they are responsible for nearly like 60% of the greenhouse gas emissions directly or indirectly. So what this really says is like, although cities are such a wedge, like such a small part of the world's land cover, like all the impacts, like all the changes that are happening, is mainly rooted in the way we urbanize, and we need to spend more, resources understanding this nexus between urbanization and climate change, particularly climate impacts on urban areas. Now, in general, there are certain hazards that are very critical for urban areas. The number one among them is extreme heat. As in later part of this presentation, we'll go talk about like why heat is such a huge issue in urban areas. But in general, like extreme heat, like is related to a lot of premature deaths in adult, very old age adult population, and also in like younger, like babies and toddlers. Also, heat creates a lot of issues in terms of infrastructure. So this is an image from North India during a heat wave where the heat actually just melted the asphalt. Also, like, the power grids are extremely vulnerable to heat. A lot of critical infrastructure is extremely vulnerable to heat. The next big deal is, of course, the sea level rise. Some of the largest cities in the world, they're coastal cities. Particularly like some of the newly developing urban centers in Asia, they're all like massive, massive coastal cities. Like cities like, like Bombay have like 25, 30 million people. Places in Jakarta, probably even bigger. So, and cities, already established cities like in Asia, like, Tokyo, and so Osaka, places like that, they're also like all coastal cities. And even in America, we have New York, who are extremely vulnerable to sea level rise. And as the sea level increases in the later part of the century, there'll be dire consequences to these coastal urban areas. The next issue is actually air quality. Now, air quality kind of has always been an urban problem. In fact, the field of urban climatology came into effect because of poor air quality issues that cities experience, way back from like, the industrial era to even like mid 1950s and 60s. I mean, cities were extremely polluted. The air quality was very poor. But lately, there is a different kind of threat that's happening. In particularly like in North American cities and also in a lot of European cities, they are experiencing extreme air quality due to forest fires. So this image is actually from the 2023 forest fires that happened in northern Canada. And the air quality was really poor for almost like a week or so. And then there was like one major event where the entire city was just blanketed by this orange smoke cover. And I think like that particular day, I think New York, which normally, has decent air quality, relatively speaking, ranked the worst among all the cities in the world. So this is a major issue. And also this year, there were a lot of forest fires making urban air quality worse in a lot of parts in Europe, actually. And then the next major thing is extreme precipitation and flooding. Now, urban areas are very prone to flooding because they replace, their permeable surfaces with impermeable surfaces like asphalt and concrete. But lately, like there have been some few cases where there has been like an insane amount of rainfall. For example, this event was in South Indian city of Chennai, which is my place where I come from, and I think this happened in 2015, where nearly 350 millimeter of rainfall, like almost like 1/6 or 1/7 of the annual rainfall, like fell in a period of less than 24 hours. The city was just like flooded, and I think it took almost like 2-3 weeks for the city to actually recover from this. A similar event happened in Spain last year. I think it was in the city of Valencia, if I'm not mistaken, where there was an enormous amount of rainfall just came through in just like a 4 or 5 hour period. There was also an event last year in New York where we received like nearly like 15, 20 millimeter rainfall in a very short amount of period, which cut all the subway and the transportation links in general. So these are some of the very extreme hazards that impact cities. Now, a lot of these, for example, extreme precipitation, like I told you, like precipitation has been a major issue, but this level of severe precipitation is becoming more and more of a normal in many places. So, cities are often experiencing immediate catastrophic consequences of climate change. So when we talk about climate change impacts, like, the things are happening right now in most of the cities, like urban people are experiencing some of these effects in their day-to-day life. It's not something in the future, it's actually happening all the time, even in, OECD countries, not just the global south, but everywhere. So I want to give now a general idea about like, what is like urbanization, like from a climate perspective. Why is it kind of like different when we from a climate perspective, and then what do we do to come to terms with some of the complexity? So traditionally, like, we can define urbanization in two ways. So for example, like any tropical mid-latitude cities, for example, you have like a natural green cover, maybe a forest cover or a crop field that is being slowly replaced by buildings, roads, steel structures, and infrastructure, so on. So on the top, on the left-hand side, you have the city of Shenzhen, and the image on the top is how Shenzhen used to look like in the 1960s or so, and that's how it looks today. So and then on the right-hand side, there's also the other kind of urbanization where in arid and semi-arid areas, Urbanization, you have the same kind of infrastructure, but also you have a little bit more greenery being introduced. So this is how Dubai used to look like in the 50s or 60s, and this is how the same street in Dubai looks today in general. So urbanization is just, large scale land cover change, and then what happens to the climate because of that, the local climate. So if you look closely, like, okay, what do these cities look like in a block scale? So one main thing you would see is there are buildings. I mean, from looking from the top, you look at a lot of different types of roofs made of different materials, a lot of green cover, grass, lawn. But then there are also like trees, mature trees. There are a lot of synthetic surfaces. And then there are some water bodies too. So it's like agglomeration of different surfaces with distinct hydrothermal properties. Now, we're looking at an area that is probably like a 1 kilometer plus one, across 1 kilometer, so a kilometer square. So within the same kilometer square, you have it's populated by so many different materials with such distinct physical, thermal, and optical properties. On the other hand, like, if you ever, I mean, when you take a plane and when you're over most of the time you just look down, it's just like, fields and fields of whether it's like corn or like a desert or ice or like, some trees. How there are like, the land cover properties do not change a lot outside of an urban area, whereas within an urban area there are a lot of changes in the materials and the material properties which have a big impact on the local climate. So now, like, what does it mainly do? A lot of the Earth's climate, one of the main important factors is the energy budget. We call it the surface energy budget. So for example, all the energy comes directly from the sun as radiation. And this radiation is absorbed by the surface. And some of this radiation is kind of sent back, like reflected back, re-radiated back into space. But then another thing happens too. The surface gets warmer, and then some of the heat is conducted down, but then quite a lot of the heat goes out as a sensible heat, like the heat that we actually feel. So here radiation is converted or redistributed as sensible heat, which is like a turbulent energy parcel, let's say. But then on the other hand, if you have a wet surface, like if there is any moisture in your surface, then a lot of this radiation is kind of like absorbed and then converted into water vapor. And then when you have vegetation, whether it's grass or trees, they also use some of the solar energy and then convert that into transpiration, like water vapor. So overall, what happens in a regular surface is like some of the energy is converted into heat and sent back into the atmosphere, and some of the energy is sent back as water vapor. Now, if you are over a forest, like a rainforest, majority of this energy is converted back into water vapor. However, if you're in a semi-arid or a desert area, a lot of this energy is converted into heat instead of water vapor. There is very less heat that gets stored in the surface. So this is how normal surface energy budget of non-urban surfaces normally work. Now, when you replace that with a city, immediately what happens is there is now very little water vapor if there aren't that many trees, because most urban materials are poor in terms of their water store, but they are very efficient in storing heat. So one major difference is like a lot of the heat is actually stored within these buildings. And so they keep emitting this heat all through the day. Whereas in a non-urban area, normally after the sun goes down, things cool up a bit. Whereas in an urban area, that's not the case. The stored energy is redistributed as heat almost all throughout the day, depending on the size of the city and the city characteristic. So that's one main difference. And then the other is in like areas like, that are commercial districts, or like, in places like New York, or, Seoul, Tokyo, in a lot of these places, there aren't that many like green cover per se. So the difference, or the partitioning between heat and water, is very much biased towards heat. So there's more and more heat. Another thing that also happens in urban area is like humans emit a quite considerable amount of heat. One main way we emit heat back into the atmosphere is when we use air conditioning systems. So if you think about air conditioning, what is happening is like the heat that is stored in the buildings is basically we are using an heat exchanger, taking this heat and putting it outside. So whenever you're using air conditioning, all it does is it takes the heat from inside your office space or residence and then dumps it into the atmosphere. And then there is also we use transportation, like anything that is non-electric really uses combustion. There is a little bit of heat emitted back into the atmosphere and so on. So anyway, so it becomes a huge sink for like heat, like in an urban area, like everywhere, everything is throwing heat into the atmosphere. I show you like a map, for example, of how much water that is in like the New York metro area. So on the left-hand side, it's actually a land cover map where blue means vegetation, dark red is medium urban areas, and then the rosy red is like a very intense urban area. Now, on the right-hand side, you look at how much water is available at the surface, and it's you can clearly see like anywhere that is urban, all the boundaries that are marked by urban areas have extremely low level of water availability. So we are throwing a lot of heat, and also we are in some kind of like if there is like a drought person or a water resource person looks at it, they would say like, oh, this area is in drought, it's that severe. So another thing is, so what we saw in these two past slides was what's happening in the surface. But the surface has a profound impact on the atmosphere, particularly the near atmosphere, like the 1 to 2 kilometer above the surface over a city is profoundly impacted by what's happening at the surface. Now, we call this as like an urban boundary layer. I'll come back to this in the next slide. But in general, there are two cases here. Whenever you have some strong ambient winds, like, the type of the boundary layer that forms, like you could see, like the darker patch, the orange patch, shows you like how much the city is impacting the atmosphere above. And you could see like some of this impact is also going to the adjacent rural areas. So cities, like particularly large cities, have a regional impact. It's not a local impact anymore, it's a regional impact. And they impact air quality, they impact cloud formation and cloud characteristics too. So they also impact like rainfall and things like that. Now, in the second case, like which is that when there is no ambient wind, this is what happens during a heat wave period, where there are these large scale thermals that just like recirculate the heat. In fact, during heat wave period, there is also heat coming from the top of the atmosphere, where we form a huge thermal bubble or a heat dome, keeping majority of the heat emitted in the urban area in the same space, creating a very dangerous situation. So if you look at some of the key challenges for urban areas, so what are the impacts of the urban area? The one is like, like what does this heat do to so much of the climate processes? And one of the, with all the climate models, one of the biggest issues is how they model clouds. It's like the case for largest uncertainty in climate models. And in an urban area, from an urban perspective, there is a lot of uncertainty in terms of like how these clouds are formed and like how does the city impact them. So this is a major question. And then there is the issue of air pollution, like how air pollution is trapped and transported. And then finally, there are issues related to like, sustainable development in urban areas. So these are some of the huge challenges that are related to urban and coastal urban environments, and some of the issues that my lab also focuses on. So in order to understand, so we have this unique climate that is created, and there are unique problems because of these different types of materials, complex land cover, and then like the three-dimensionality of the urban areas, the anthropogenic activity. So how do we bring these things to scale? Like how do we advance our knowledge of climate processes in an urban area? So before we go there, I wanted to just share this one screen, which is like there is a concept called a boundary layer. A boundary layer is just the layer of the atmosphere that is actually impacted by the surface. So for an urban area, we call it as the urban boundary layer, which is normally like a kilometer or two over the surface, and which is kind of like, during the daytime, it's much deeper. And then during the nighttime, it comes down because the atmospheric turbulence kind of like regulates the depth of the boundary layer. And understanding the boundary layer is very, very important for issues like heat, clouds, air quality, and so on. And it's pretty much the focus of a lot of the work that I do. So the way we study the urban boundary layer, the boundary layer is a very classical fluid dynamics concept. We know about this boundary layer from like the 1910, 1915. And it really revolutionized the aerospace industry. In general, like in classical physics, they never cared about the area they thought like everything was very uniform. And then there is a guy from Germany comes up saying we have to really think about this small space about any surface. And so there's a lot of classical fluid mechanics theory related to like how we understand the interaction within this boundary layer. And these advancements have been brought into our urban climate area too. So instead of having just like a flat plate, we just put a city in there, and we use some of the very classical framework to study or understand the urban climate in general. Okay. So, and also physically, that's from the theoretical perspective, but from an experimental perspective, like what we do is we obviously use a lot of traditional tower-based measurements and ground-based remote sensing measurements, like using LiDARs and radars and weather monitors around, different areas. And then we use a lot of computational fluid models, just like your global climate models. There are regional and urban climate models that we use to study the urban area. And then another area that is gaining a lot of importance within the urban climate community is the use of remote sensing, which is like using space-based satellites, geostationary satellites, cube satellites, in order to advance urban climate processes. So to give you an idea, some of the infrastructures that I've worked with. So in the first one, you see like a traditional flux tower. This is one of our instrumentation setup I think this was in Maryland for an experiment. And then here on the right-hand side, this was an experiment we're doing at Princeton, which uses like a scintillometer, basically shoots a laser, which is able to sense the change in heat. And so we can understand the heat flux from the surface. And then below that, you see like a radar and an acoustic profiler, which measures temperature and wind speed in the atmosphere at different heights. And then we also down here, we have a distributed weather network in New York, where we have like weather stations at different parts of the city, so that we have a better understanding of spatial gradients, which are very, very high. And then there's also like newer technologies now where we can use like unmanned aircrafts or drones fitted with instrumentation to measure weather and basic meteorological variables, which are very, very useful for urban related work. Again, this gives a map of all the sensors, the regular weather stations and enhanced weather stations that we have in the New York area, which we use a lot for our research. The second aspect is the CFD modeling. So now I want to give you a good perspective of what urban scale modeling is. So on the very left-hand side, this is a global scale model. Normally, global climate models are run at 1 arc degree, which is around 102 kilometer by 102 kilometer. So if you think about it, the smallest area a global climate model can resolve is like 102 kilometers. So, from a global climate perspective, let's say if you're looking at something in the Arctic area, like, in the Scandinavia, like that's how much you can resolve. Like, that's the resolution that you get. But then there are other things. There is a regional climate models. Regional climate models are, they have scales around like 10 kilometers to even like 3 or 4 kilometers. So they are much better results. So here they are really good to study, like, regional impact. So you can see in the middle part, like, the resolution is now a lot better. So you can see like what's happening like in different regions of a particular area. But then for the urban one, you have to go even more finer. So on the very right-hand side, you see an I mean, this is an extraordinarily high resolution urban climate model where you could literally see like what's happening at block scale, looking at a city in general. So this is the level of granularity that we need in order to study urban physics. So from a computational perspective, like urban modeling is a lot more intensive compared to global. I mean, global climate modeling also has their own complexities, but in terms of like what you're resolving, you have to use a lot of computational power to get here. So how we model cities is in this very interesting and abstract way. Like in all these models, cities are basically represented as like two buildings and then a road, a street in between. So the cool thing about this is a very simplistic pseudo 1D model which you can use to study a lot of urban effects. So in here you can see like all these resistor things. They are basically telling you that we call them as aerodynamic resistance, like how much like a surface is coupled to a particular place in the urban area or in the lower atmosphere. So this particular model you can absorb human activity. So here, like, traffic, energy used in buildings and the heat released from buildings, and also pollution released from buildings can all be brought into the same framework. So this is how cities in general are modeled within an urban climate model. The next aspect I want to show you is the urban remote sensing. So normally, satellites, a lot of the satellites traditionally have been like polar orbiting satellites. So they take a snapshot at one part of the Earth, and then they keep on moving around the Earth, taking pictures of different areas, which is like nice. But in order to do some really like urban meteorology, it would be really helpful, like if you have a satellite that's just sitting there. And that's what's been happening lately. There are a lot of geostationary satellites popping up, which normally focus on one part of the world. So for example, sorry about that. This is a GO-16 satellite, which is a NOAA operated satellite, which sits on top of the US, and it captures some of Canada, Mexico, and the US. And then it takes an image almost like every second or every other second. And using this, we can do quite a lot of things in terms of like urban climate stuff. So this is a new area that is up and coming. So now I want to go and talk about like, using these tools, like what we have kind of learned, some of the interesting results. So the first one I want to really focus on is about the heat and what extreme heat and the city is all about. So this is our work that we did maybe like 10 years ago or 12 years ago about the impact of heat waves in northeastern United States. And we did an urban climate simulation for like a whole summer period over multiple cities in the US. And one important thing that we found out was we all know about this effect called urban heat island. Basically, like, urban areas have these materials that produce or store a lot of heat energy, so they're normally warmer than the surrounding environment, and we call this as the urban heat island. So one thing we found in our work is like the larger the city is, particularly in the Northeast, the larger the urban heat island effect is. So for example, in New York City, the average temperature is almost like 5 degrees Celsius, which is quite a lot. warmer during the summer months than the neighboring area. But however, if you are in Rochester or Bridgewater, the impact is much less pronounced, only around like 1 to 2 Kelvin and so on. We also saw, like, we were also simulating the 2006 heat wave in Europe that led to nearly like 40,000 deaths all over Central and Northern Europe. And here in our simulation, we found very interesting results. What we found was during these heat wave episodes, the coastal cities tend to have much higher, experience much higher temperatures. And one of the main reasons is like the oceans are a huge moderating influence on a city's climate. But then during some of these heat wave events, we lose that moderation because of change in wind direction or lack of wind. So they are not effectively cooled by the ocean. So the temperatures are like increase much, much more. And some of this we see even in the US, where in New York, for example, during the heat waves, you do see like an increase in the urban heat island intensity, mainly because of we lose the sea breeze intensity. Another important things we wanted to know was like, okay, so we know that urban, like people contribute a lot of heat, put a lot of heat back into the atmosphere using air conditioning. But how much amount of heat can you credit to or attribute to human beings and human activity? So in New York, what we found is around 12 to 16% of the heat in the lower atmosphere or the urban boundary layer is directly related to air conditioning use. On the left-hand side, you see like what's happening during a normal day, like how much heat is put back into the atmosphere. And on the right-hand side, you kind of see like during a heat wave situation, how amplified the issue becomes. Now, one of the most interesting thing here is as heat waves put a lot of stress on the power grids. And in a lot of places, particularly like in places like India, during these extreme heat periods, they also don't have any electricity. And this is also happening more and more in Western countries. Like, for example, I think like last year during the summer month, or this year during the summer month, the power grid in Spain kind of broke. And apparently there was a forest fire that burnt one of the main transmission lines, and almost the entire Spain was without power. And this happens in a lot of areas, like even in New York, like certain neighborhoods lose power during extreme heat. And it happens in the tropics in Caribbean. I was part of a project in Puerto Rico where they normally do not have any air conditioning in schools. Traditionally, they used to have like 2 to 3 weeks where the temperature would be really bad, so they can just like close school. But I think like in 4 or 5 years ago, they had nearly like half the year where the temperatures were absolutely horrible. So this is becoming an increasing problem. So the heat puts a lot of stress on the power grid. Another interesting thing is this is a work that we did in Beijing, where not only heat, but sometimes you can also have more water vapor in the atmosphere because of anthropogenic activity. So a lot of the air conditioning system in commercial buildings use this thing called a chill water reactor. So basically it's like a cold water where the heat is transmitted into like this cold reservoir of water, which then evaporates. So this heat is converted back into the atmosphere. And we found that in Beijing, since 2000 or so, they have like built large commercial structures, and there's been like an increase in anthropogenic water vapor in the atmosphere. And then finally, and this is one of the main links, where it tells us like how much heat is stored in the city. So the image that you see here is actually our model using the satellite data GOES, where we computed like how many, like in every 2 kilometer, 1 kilometer pixel in New York City, how much energy is actually stored. So New York City, particularly in the summer months, is a net store of heat, and this heat gets like radiated back into the atmosphere. And also, the more the storage, the more the electricity demand too. And we also found like this is one of the reason why larger cities larger and dense cities experience more urban heat island because there is just like more heat stored. There's the capacity to store heat is what makes the urban heat island even more intense in larger cities. Another thing I want to mention is like, so the heat that we all emit, also like during a heat wave period, there is heat coming from the top of the atmosphere. So just like how when you have like, a cyclone or a storm, which brings water vapor, a heat wave is just an anti-storm, which brings heat instead of water vapor. So one of the things that happens during these heat waves is there is a huge thermal block. There's heat coming from the top, heat coming from the bottom, and there is no relief for this heat. It just keeps circulating within this urban area, which makes things very worse. And that's exactly what causes a lot of heat-related deaths and infrastructure failures. Another thing our urban climate models can do is like, unlike a global climate model where people can run a global climate model for 100 years. You start the simulation right now, and then you can see like how the situation changes for different scenarios, and then look at like what happens in 2050, 2075, whatever, 100 years later. But the urban climate models are normally very expensive to run. So most of the time you're running it for like a few days or maybe a few weeks, but no more than that. But one cool thing you can do is that you can take a global climate model, take that data and fit it into your urban climate model and then see what happens in the future of cities. So here we took a global climate model and then ran that for different scenarios for New York and for different RCPs, representative climate pathways. I think now these are called like a different like social pathways or SSPs, I guess, RCPs or SSPs now. Some of the interesting things we found is the number of days New York is going to experience extreme heat period is going to tremendously increase. In fact, one of the alarming results we found is in the later part of the century, if we carry emitting the same way we are, our summers will begin in April or May, and they will extend till the end of September or even till October. Now, that is adding a huge amount of strain on the people, plus also on the energy side of things. Because normally, if you're living in like, mid-latitude, like New York or even like, Toronto or any of these places, you could see your lowest electricity bills are between April, May, and then in September, October. But then what this means is like you're never really going to have any shoulder seasons. Like our like spring and fall are going to just disappear, and we're just going to have like really bad intense summers and maybe like bad winters. The next issue I want to talk about is like rain or particularly like thunderstorms. Now, because of how significant like heat has been, there's been a lot of work done on urban areas and heat, but relatively lesser on the issue of rain, particularly like thunderstorms. And we had an opportunity to look at how cities impact thunderstorm formation and thunderstorm effect in Houston, Texas. And we used a lot of observational infrastructure and also like some modeling to actually like look into like what does the city do to the thunderstorms. One of the biggest issues is like there is this big question since the 1970s or 80s, which is like, do cities increase the intensity of thunderstorms or do cities decrease the intensity of thunderstorms, which hasn't been really answered by the community. So that was one of the things that we set up to answer in this work. And some of the interesting things we found in our work is, so these are all like observed results. We're looking at like how the sea breeze really like impacts the climatology of Houston. So in the series of images you see here, SBF stands for a sea breeze front. So 4 hours before the sea breeze front, so this is like maybe like 7 o'clock or 8 o'clock in the morning, you can see like there is the temperatures are pretty low they're blue in majority of the area. So the purple patch is your Houston city, and then the other areas are mostly like rural areas. But then as the day starts warming up, you can see like the temperature becoming hotter and hotter. But then when the sea breeze starts forming, you can see like there is in the middle row, you could see these blue spots, the cooling spots that appear. And it's basically all this like wet moisture from the ocean that is getting transported, and it creates your secondary circulations. In fact, in Houston, it's the sea breeze that creates the urban heat island effect. For example, like in the same area on the left-hand side, you're looking at days where there were no sea breeze, and you could see like almost all the temperature between the urban and the non-urban areas are pretty much the same. The urban impact is very, very low. However, the sea breeze, on the other hand, is what sets up the climatology of Houston. And we found like this is one of the most important features if you have to study thunderstorms, because thunderstorms need a lot of heat that is produced in the city. And also it needs a lot of moisture that is, in this case, coming from the ocean. So what does this kind of like soup concoction make? I'll skip this slide. But one of the things here, you're going to, oops, sorry. Okay, that radar image is not working. But anyway, so let's move on to this. So there are three effects that we identified that a city does to these thunderstorms. One we call as the bifurcation, or the coastal bifurcation. So on the top half, you see like the thermal structure of the city. And on the bottom half, you see radar images of these convective clouds that are moving into the city. Now, the city sometimes, when it's able to split these storms, so you could see like these patches of big convective storms that are coming into the city, and they're following the storm front, but then the city can split them. And so there is a chance, depending on the direction of the storm, they can split or bifurcate the storm. And so the city receives lesser rainfall. The second thing we found is because sometimes these things are split, and also depending on the wind direction, the city like pushes all these convective storms to one side of that is outside the city. So in this case, for example, in Houston, one of the area that receives a lot of rainfall is the northwestern part of Houston. And one of the main reason is because the city actually splits a lot of these systems, and also creates a bigger pool of these convective storms at one side that relates to extreme rainfall that happens on the northwestern part of Houston. And then the final case is the other thing that's responsible for this downwind enhancement is we call it a deflection or barrier deflection, where the city creates a very, there's a lot of buildings and there's a lot of aerodynamic roughness, which creates a barrier-like effect. So some of this convective activity, depending on its intensity, tries to avoid the city and then moves around or curves over the city, which also creates a lot of rainfall in the suburban areas that surrounding or the rural areas that is surrounding Houston. The next thing I want to focus is on air quality. Air quality, like I told you, you can split it into different scale. There's like global scale issues, which are related to forest fires and so on, and then regional scale. But then there is also city, neighborhood, and building scale. So for example, a lot of people who suffer from air quality are people with like respiratory illness. And in New York, which you will see, I'll explain in the next couple of slides, where the issue is because of poor housing quality. So a lot of older people and babies, they stay inside homes where they have really poor air quality. So whatever air quality that work that is done, it has to hit all these spots, from all the way to global to the building scale in general. So one issue that we find is like air quality, unlike water vapor or heat, is like sparsely distributed. So we need to have like a good spatial representation for different air quality. So in this case, let's say we talk about particulate matter or ozone, which are two major pollutants of concern in New York area. Like you need to have like better spatially represented measurements. The satellites don't do that. And we also find like a lot of models, the traditional regional scale air quality models don't do that too. So in order to improve this, what we have done is like we do this like street scale measurement, where we have students who strap on a backpack, they put on these research grade instruments that monitor particulate matter and ozone, and they took multiple walks. So we took around 40 to 50 walks. So this happened in 2023. in New York area, all these lines show like where these walks took place and so on. And what we find is, one of the things that we find is pretty interesting with respect to ozone, which is a big issue in the summer months. Majority of New York is under the same ozone climate. And so it's actually a little bit easier to predict. Whereas on the other hand, PM 2.5, which is a very important pollutant, is a much harder thing to do because there is a large scale spatial variability in it. So we came up with a modeling environment. We took the same urban climate model, but then fitted in some chemistry into it in order to understand urban climate at a much better scale. Until now, all I can, in some of our work, this is ongoing work here, we see like our model can resolve air quality at scales that are representative of the urban environment. So here you could see like a prediction by a NASA GEOS system and a NOAA system and our own urban WRF-Chem system. And normally our performances seem to be a lot better for city as well as regional scales. And these are our measurements verified or validated using aircraft measurements. And overall we have like we have a model that is now capable of forecasting air quality at much better spatial scales. What else I want to say? Oh, and the final thing is like everything that we do involves people. And this is another interesting issue with urban climate work is like you're constantly dealing with communities or people who are, very much vulnerable and impacted by these effects. So in 2015, we teamed up with WNYC, which is a local radio station, in order to do a broadcast program where we distributed air quality, indoor heat sensors to different houses in Harlem area in New York. And then the radio station interviewed people to know their lived experience, like how they are experiencing the heat wave, and then we can objectively see like what's happening to the temperature in the background. Now, some of the interesting things we found out in this campaign was, unlike the outside environment, the inside temperatures do not change too much all day. So you can have a non-AC apartment which can experience like 80, 90 degree, 90 is almost like 30, 31 degrees Celsius all through the day. And the other interesting thing we found out is even after a heat wave, so this is like almost a 2-week period where we had like an intense heat wave. So the temperatures are increasing. The blue and the red ones show you the indoor temperatures of apartments with AC, which is the blue one, and then no AC, which is the red one. And then the grayish one tells you the outside temperature. As you can see, the outside temperature is varying too much, but the inside temperature, if you have AC, much lower, almost like 10 degrees lower, whereas the indoor temperature when you have no AC, much, much higher. But most importantly, the indoor temperature never comes down even after the heat wave ends. So in New York, for example, once the outdoor temperatures are brought back to normal, they would say the heat wave has ended. So no more emergency warnings. However, if you are living in an apartment which does not have proper air conditioning, you are still living in an heat wave-like atmosphere. And we also found like there is a lot of deaths, particularly in like late heat waves that happened during this period. This project led to like the government wanted to step in, and they started a program where they were providing like air conditioning assistance to low income people in New York. And I think there are at least like a few thousands of them, maybe like 5,000, 10,000 people or residents in the city, which use this opportunity to have air conditioning in the summer. Another thing we also found, which was really bad, was whenever the heat was very high outside, the air quality, the indoor air quality was also extremely high. And this is like, compounded extremes. And then finally, like, another thing we did is we went to India, and then we made, like, we wanted to see, okay, we do a lot of work in America, but what do like people in India, like, how do they experience it? So in Chennai, for example, experiences really, really harsh weather starting from like May or even April these days to almost the end of August, where the heat index could be almost like 130 all through the day. So we went to India to actually talk to like regular working people who actually work on the streets. And then like we wanted to know like how they experience heat and what they think about it. So I'm going to play the trailer for this movie. So this movie is currently doing all the film festival circuit, so it's not available for public consumption yet, but I could show the trailer.
எனக்கு ஃப்ரண்ட்லயே இருக்க சிலிண்டர் இப்படி எம்டியா இருந்தாலும் ஃபுல்லா இருந்தாலும் அந்த வெயிலோட 100 டிகிரி அது மேல படுத்துன்னு வச்சுக்கோங்களேன். அது இன்னும் முகத்துல அடிக்கும். பயன் பண்ணும்போது அனல் அடிக்குது, சட்டையெல்லாம் டைட் இது பண்றப்ப எனக்கு வர வயசு ஆகுது இல்லை, மூச்சு வாங்குது. ஃபர்ஸ்ட் தான் 200 150 அப்படி இருந்தது. இப்போ 300 350 400 வரையும் போகும். அதாவது ஒரு ஆர்டர் லெவல் கீழே இறங்கி
இருக்கிற பெரிய பெரிய ஸ்கூல்ல வந்து ஒரு கார் எடுத்து வராங்க. அந்த கார் பார்த்தீங்கன்னா கிட்டத்தட்ட வந்து ஒரு 15 அடிக்கிட்டு இருக்குது. இதால டிராபிக் இது அதிகமாகுது.
எப்படி இந்த வெயில் அதிகமாகிட்டே போகுது, அது எதனால நினைக்கிறீங்க நீங்க?
சரி, சித்திரை வைகாசியம் ஃபுல்லாவே அப்படிதான் இருப்போம் நம்ம நினைச்சுக்கிறது.
அழகே மாறுத, நம்ம என்னத்த சொல்ல முடியும்? நம்ம பச்சைகரம்
ஓசோன் லேயர்ல ஓட்ட விடுது அப்படின்னு சொல்லி சொல்றாங்க.
All right, I'm going to stop at that. I think I've taken
enough. Thank you so much for this amazing overview. I mean, just so diverse and really fascinating research and insights. Really important work as well. We're at the top of our hour. I'll open it up for maybe one question if anybody has anything. From my end, I mean, I'm very interested in kind of understanding, you know, what some of the most promising or evidence-based kind of design and policy strategies that cities can adopt to really moderate heat, you know, improve air quality and reduce vulnerability to extreme events are, you know, from a policy recommendation standpoint. Could you maybe comment on that before we close off for the session?
So I think like in some of the Asian cities, particularly like places like Singapore, they're really on top of what needs to be done. So they have a lot of passive mechanism to moderate heat. They have like a lot of passive cooling stations. They have city codes that tell you like what type of material that you have to use to build. And also they're increasing like, you know, trees, and also mainly trees also provide a lot of shadow effects in general. And I think Singapore is a really good case because a lot of the new urbanization is happening along the tropics with like very similar, you know, climate. And so like, you know, so that's a city that's really on top of what they want to do. And then I think there are a lot of like European cities, for example, they want to reduce the you know, people who drive to work. And then there's also some other arrangements where they are giving people extended holidays during the summertime, because then they don't have to come to work, and commercial work actually uses more energy, more heat into the atmosphere. So that's another way to think about stuff. And then in some parts, they're really like rearranging the way they operate. Like I know like in Middle East, for example, like people don't have to work after like during the summer months, like after 1 to 4 or 5 p.m. And this is also the case in southern India right now, where workers are given a break between like 12 to like 4 or 5. So they start very early in the morning, like around 5 or 6, and then work till 11, and then they take a break, and then they come back in the evening. So all these things are happening at different levels. And this type of adoption is happening, you know, in general, particularly in the developing world, and also mainly in Europe.
Wonderful.
Yeah.
Wonderful. Thank you so much, Pratap, for your fantastic presentation. The epidemiologist in me will be in touch just to think about how we overlay some of this with health related data. Again, as a reminder for everyone, all of our science talks are available on our UNU-INWEH YouTube channel. And we look forward to seeing you again next week for our next science talk.
All right. Thank you. Thanks everyone.
Everyone.